We can find the mistake in proofs by checking with small examples and type checking every line in the proof. Let's prove a Fick theorem. The sum of any two even integers equals 4k for some integer k. I don't think this is true. So the proof goes, suppose that m and n are even integers. So let's try m equals 0 and n equals 2. By definition of even, m is 2 times some integer, so 2 times 0 for k equals 0. And n equals 2 times an integer. Oops, this is trying to use k again. I need to change that for some integer k prime. And then it says m plus n equals, 2k plus 2k prime is just 2 times k plus k prime. This shows what the problem is. We have reused k for two different values. And what we gave was already a counterexample to the theorem, proving a real theorem. For all positive integers k, the value k squared plus 2k plus 1 is not prime but composite. Recall that numbers are composite if they're the product of two positive integers. Let's check what we understand this. If I use k equals 1, then I get 1 squared plus 2 times 1 plus 1 is 4, which is 2 times 2. The proof does, the k equals 2 case, finds that it's 9, which is composite, but then it claims the theorem is true. I'm supposed to prove for all positive integers k that this, not just for one example. Let me do another example just to see what's going on. 3 squared, which is 9, plus 2 times 3, which is 6, plus 1 is going to be 16, which is, hey, it's a square. 4 is a square, 9 is a square. If we just look at any positive integer, k greater than or equal to 1, we're going to have k squared plus 2k plus 1, which just factors as k plus 1 squared. And so, for all integers, we just get a square. Now, k plus 1 has to be greater than 1 for the number n to be composite, which means that k has to be greater than 0, and so for positive integers. The proof is basically this. An adversary gives me an arbitrary positive k, and I factor the expression, and then argue that this really is the product of two numbers that are greater than 1. Symmetric and transitive. Here's a proof that every binary relation that is both symmetric and transitive is also reflexive. What does this mean? If I have a relation that's symmetric, if A is related to B, then B is related to A. And by transitivity, if A is related to B and B is related to A, then A has to be related to A, and similarly B has to be related to B. So this seems plausible until I put down C here and don't connect it to anything. I'm supposed to provide a counterexample on 0, 1. The empty relation on 0 and 1 would be symmetric and transitive, but not reflexive. So where does the proof break down? If I just think about either one of these simple examples, for all x, y, and x is related to y implies y is related to x. And transitivity holds vacuously because the first part of an if is never satisfied, and so this statement is true. So for any x related to y, here's where the problem comes. We don't have x related to any y, and this is just assuming that we do to declare that x has to be related to x. So the problem is here. I'm assuming that 0 is related to something, and if it's not related to anything, then my proof breaks down. So that's the type checking, that's the problem. The next two are one-way airlines. There are two videos introducing the problem and describing an induction proof for one-way airlines. A student in one class tried to prove that for all n cities, every city can be visited. And he tried to use this as the induction hypothesis. Well, we already have a problem here because it's not just cities, beyond the misspelling. It's not just cities that we're giving. We're given a map, a route map, that between any two pair of cities flies one direction or the other, possibly both. So we're given a one-way airlines map, not just given the cities. And this is important to assume that we're given a map, so that we get to assume in the induction hypothesis that there's a specific map that we're talking about. The induction hypothesis also has a problem. It assumes that there is a vertex with no incoming edges, but it's very easy to make maps where every vertex has some incoming edge, and it is an OWA map. And so step 5 is trying to change the types of maps that the proof applies to. It only applies to the ones with no incoming edges, so it won't apply to all maps. Step 1 isn't even specific about that we're dealing with OWA maps. You want these things to match up, and you want one to include everything you're going to need in the induction hypothesis to be able to supply you what you need for step 7. Here's another attempt at a proof where the mistake is going to be in step 7. So we're given a route map. This is good. That's bigger than the base cases. Again, I'd really like to assume that for an OWA map, that all cities can be visited without interruption, arriving, departing more than once. We want to prove for a given map, that's good. Let's call this an OWA map again, that all of the cities can be visited without breaking the rules. Okay. If we take any number of cities, n greater than 2, we don't need to do this. We're already given the map, a specific map. We can create a path which connects each in such a way that none is visited twice. Now wait a minute. This is what we're trying to prove. This is not the induction hypothesis. And we're trying to prove it for a specific example with n greater than or equal to 2 cities. The induction hypothesis only lets us assume it for k's up to but not including n, because otherwise we're assuming what we want to prove. So don't assume what you want to prove. If we always include a flight from the last city back to the first, it will... Wait a minute. This isn't necessary at all, nor is it always possible. If you say, if we do something, check that it can actually be done. So just because you have an idea, don't throw it in there. Leave it on your scratch paper.